Okay, I think we're ready to roll. Yes, we're ready to roll. Last day of class, isn't that unbelievable? I want to start off with talking about the exam for tomorrow. So I've decided a slightly different approach to the exam than we normally have. I have written a 12-problem exam. Some of them are pretty short and pretty easy. Some of them are going to take you a little bit more time. So obviously, like before, always take advantage and do the easy problems first. This is the approach that I'd like to take. So it's 12 problems on the exam. You choose 10. You can choose whatever 10 you want to. So you can go through, you can solve them all if you want to, if you have enough time to do that. And ultimately, you're going to cross off whatever 2 you don't want me to grade. If you don't cross off anything, I'm going to grade the first 10, and then I'm not going to count the last 2. So it gives you an option. So that way, if there are a couple of areas that you struggled a little bit and you're not real sure of yourself, you can skip a couple of different problems that you're a little less sure of. So we'll do that tomorrow on our exam. Our exam will start at exactly 12. I'm not opposed. I don't know what the rest of you have for tomorrow, but I don't think you have any other classes during that time. If we need a little additional time, I'm not opposed to going an additional half an hour. But we'll play that by ear tomorrow. We'll see how that goes. Okay, so that was 1. Number 2, let me go to yesterday's lecture. And let me make sure I get the right one. And it looks like 423, 23, 24. Yesterday, that one. So, scroll down to the bottom. Right here. This is where I made the mistake. I told you I had a mistake in there, and sure enough. So when I multiplied through by 2s, I said in here I was going to multiply inside instead of outside. And so I did multiply by 2s on the inside, but I still multiplied by s on the outside. So we ended up with an extra s there on that term. So it should disappear on that line. It should disappear on this following line here, all the way down to here. That'll clean this up, and that'll look like this, which gets us down to this, which is exactly what we put down here. So that's where the mistake was. So I'll give you a moment for those of you who have your notes, if you want to go through that and just make those changes in your notes on those lines. This was the last problem that we worked yesterday. Those are the changes that should be in your notes. Okay, Connor, you gave us 2 problems yesterday. This was one of them.
Yes, and then other one was 30.
30, okay, excellent. Problem number 30. Okay. Problem 30, there's no energy stored in the circuit, so let's go back here to today's. Is this today's? Nope, that one's not today's. Let's get the right one. That one is today's right here, it should be. Okay, not sure why it's not there, but here we go. So today's date is 28th or 28, 2020. Okay, so we're looking at problem number 30 in our book, and there are multiple parts to that as well. I'm sure I didn't ask you to do B and then C. It's probably, I'm guessing for problem number 30, it was A and D. Is that what I asked for, A and D?
A and C.
A and C. Determine if the results above 1330. That probably should be A and D. 1330. Did I assign 1330? I don't know. Regardless, I don't know if I signed 1330. Doesn't look like one that I signed. Five ohms. 25. RG. 25 henries. Capacitor. The capacitor is 20 milli, and then 20 IC up the top here. Dependent source. It's plus 20 IC. Okay. It feels like, which one did we do yesterday? This feels like the one we did yesterday. I don't know. Okay, so I would say if I told you to do U of t, let's get that in there. If I told you on 1330 to do A and C, it would have been A and D. So that would have been a mistake because C pertains to B, and that's using the initial and final value theorems, which I didn't go over with you. So here we want to do A and D. Okay, so for this, what are we looking for? We're looking to solve for I0 of S. I0 is over here. So there's I0. This is I phi over here. Let's differentiate between those two. So we want to solve for I0 of t, and before that, I0 of s. Okay, so you quickly look at this, you see that there are three boxes to this structure. So if we were to solve for this using mesh analysis, there's one current source, 3 minus 1 is 2. So there would be two equations. If we were to look at this from nodal analysis, there's a node here, there's a node here, there's a node here, and a node on the bottom here. So there are four. Here's a supernode from here to here. That's all a supernode. So one reference, that's going to give me two equations. I'm solving for I0. I0 would be challenging to solve if we did nodal analysis, so I'm going to choose mesh analysis. So with mesh analysis, first of all, let's convert the circuit. So here we go. 5 stays 5. IG is 100 U of t, so IG is going to be 100 over S. This is going to be 25S. This is going to be I0. This is 20 I phi. This is I phi. And then 20 milli. 20 milli is, just a reminder, 20 milli equals 0.02. And so we want 1 over CS. So C times 0.02. 1 over 0.02 is 50. So it's 50 over S. That's my C, S. So that's going to be 50 over S. So this is 50 over S. Okay. The math will be ugly math. We're just going to work with it. We're going to deal with it. Whatever happens in the math, just hang tight. Don't worry about it. All right. So I'm going to try to make sure I isolate this current up here. This current I0. I'm trying to make sure I isolate that. So it looks like 1, 2, 3 elements this way, this way, this way, 3 elements. So I'm going to identify IG, and I'm going to do this with IG. IG, but we said IG was, let's put it in there. It's 100 over S. And then I'm going to put this loop in here like this. And let's call that I1, and then this one around here, and that'll be my I0. Okay, so let's start to write the equations. So at I1 starts over here. I have 5I1, it's the only current through there, plus 25. Now it's going to be I1 minus I0, plus 25S, and that's going to be a lot of them here now. Ready? It's I1 minus I0 plus 100 over S. And then the last term is plus 50 over S, and that's going to multiply I1 plus 100 over S. Sum those all up and they're equal to 0. Cleanup time. So let's see, for the I1s I have, actually I can divide by 5. It's 5, 5, 5, 10. Let's do that right now. Now, let's add my I1s. So I have 1 and 5 is 6. So I have 6 plus 5S plus 10 over S. All of that multiplies my I0 terms. I think it's all going to be negative here. So let's take a look. I have negative 5 minus 5S, just those two. So minus 5 times S plus 1 times I0 equals, now the 100 over S term, I'm going to bring that to the other side of the equation. So I have 1 here, 1 here. So bring it to the other side, it's going to be negative, and then I have 5S plus 10 over S. I'm going to factor 5 out of that, and I probably should, all times 100 over S. Woof. Okay, so let's at least multiply through by 1S. We could multiply through by 2 if we wanted to get rid of all of the S's, but I'm just going to, right now, I think 1S is going to do the trick for me. So let's multiply this times S. And so when we do that, we're going to have 5S squared plus 6S plus 10 times I1 minus 5S times S plus 1 I0 equals negative, I'm going to pull 5 out, and then I'm going to have S squared plus 2, all times 100 over S. So there's our first equation. Okay, let's try to get our second equation now. So the second equation comes from this loop up here. Let's leave it low enough so that we can see it. Actually, just squeeze this in a little bit that we write this equation. Okay, so this is I0. So we have minus 25 feet plus 25S times I minus I1 minus 100 over S. And we have plus 25. And that 25 is going to multiply I0 minus I1. And those are the terms in that loop. Sum them up, and they're equal to 0. Okay, you can see clearly we can divide through by 5. Let's do that. It's going to give me a minus 4, a 5, and a 5 right there. Let's write these terms. I1's first. So I have minus 5I1 and then minus 5s. So minus 5s plus 1 I1 plus minus 0 terms. Same thing. 5 times s plus 1 I0. And then I have this minus 4 I phi, so we're going to need a constraint equation for that. And all of that, sum that up, and that's equal to, on the other side, and this is going to bring that over to the other side. So it's 5s times that 100 over s. So that the 2s is going to cancel. It's going to be 5 times 100, which is going to be equal to 500. Okay, so now we need our constraint equation. We have not written the constraint equation, so let's come up top here. Let's write our constraint equation. So the constraint equation is for I phi. Go in the circuit, find it. Here it is, found it. I phi is equal to I1 plus 100 over S. Bummer. Okay, so we're going to put that in for I phi. So this is minus 4 times I1 plus 100 over S. That's that term. So let's group this again. So we're going to end up with another minus 4I1. So right now I have 5S minus, I have negative 5S minus 5 minus another 4, minus 5S minus 9. I1 plus 5, S plus 1, I0 equals 500, and then I have to bring this other term over, and that's going to be plus 400 over S, or plot of 100, 5 minus 4 over S. Okay, that's our second equation. We're solving for I0. So let's slide this up a little bit. Solving for I0. Whenever you're in Laplace world, you don't want to screw around too much with substitution or elimination. In Laplace world, it's usually going to be easier if you take your information that's there and go right into Cramer's rule. So let's go ahead and go into Cramer's rule. So I0 equals, let's see what we have in the denominator. 5s squared plus 6s plus 10. I can see the ugliness coming up. Minus 5s, s plus 1. Minus 5s minus 9. And then 5 times s plus 1. So that's the denominator. In the numerator, we're going to make the substitution, the appropriate substitution in the second column. 5s squared plus 6s plus 10 here. Minus 5s minus 9 here. Actually, let's do this. Then we have, goodness gracious, what a mess, minus 5s squared plus 2 times 100 over s. That's not pretty. This one's ugly. I can see this one's really ugly. And this is 100 times 5 minus 4 over s. Okay, here comes the ugly math. So 5s squared plus 6s plus 10 times 5 times s plus 1 minus a minus and a minus 5s, s plus 1, and then 5s plus 9. So that's the denominator. The numerator is even worse. So it's 100 times 5s squared plus 6s plus 10 times 5 minus 4 over s minus 5 times 100, 500 over s times s squared plus 2 times 5s plus 9. Wow. And that's not real pretty at all. Okay, so just carrying through on this here. Don't even know what to do. Let's do this. Let's multiply by s over s here. We'll just get an extra s term in the bottom. This will give me the following. It's 100. And this is going to give us 5s minus 4. So I'm just going to multiply the s in the top through here, through that term, s over s. And then 5s squared plus 6s plus 10 minus that s cancels with that. S in the denominator there, s squared plus 2, 5s plus 9. There's a lot of multiplying through that I don't feel like doing, but it's nonetheless, it's there. And the denominator, I'll pull this 5 all the way out. So that's taking care of that 5 and that 5. And now let's see if we can start to multiply through. So I have 5s squared. And then I have, I'm sorry, 5s cubed. 5s squared, 5s cubed. Then 6s squared plus 5s squared plus 11s squared. And the s is 6s and 10s plus 16s, and then plus 10. Minus, remember there's an s out here, so we're going to multiply by the s afterwards. So first I get 5s squared, and then times s, that's 5s cubed. And then I have 9s and 5s is 14s times s is 14s squared. And then I have 9, and then that 9 times s is going to give us 9s. Okay, let me focus on the denominator. So there's a 5 down there. Actually, let's take that 5 and put it up top. Let's get rid of that 5 in the denominator. So we don't want that there. Now, 5s squared minus 5s cubed minus 5s cubed, gone, beautiful. Then we have, let's see, 11s squared minus 14s squared is minus 3s squared. Take care of that. And this is actually all in the denominator, just looking at the denominator here. 16s, let's put that, let's get this down there, minus 3s squared. Okay. 16s minus 9s, 7s, and then plus 10. Okay, so this is not a pretty function at all in the denominator. So why is it not a pretty function? Because we do partial fraction expansion right there on that denominator. Don't worry about the numerator. We know how to play with the numerator. We're going to do partial fraction expansion on the denominator. There's something else that's interesting that's taking place with this cancellation of the 5s cubed that occurred in the denominator. We now end up with a fraction here. And in this fraction, we don't have a strictly proper rational fraction, so we're going to have to divide through. It's going to be ugly. It's going to take a lot of time, and I'd rather spend more time on other problems. But here's if you get to this in the denominator, you've got to pull this 3 out. Then you have to do this. So pull out a minus 3, s squared minus 7s minus 10, 7s, 7/3 s minus 10/3. And now you're going to use the quadratic formula to factor that, to get that into your factored terms, to see what your factors are. And all the math is ugly, but it's math nonetheless. So don't worry about the math being real ugly. It's not that bad at all. I don't think I assigned that problem. Let me just check mine. I tried to avoid ugly problems. So I did not assign 30. So you're not responsible for that one, but nonetheless, it was a good exercise to go through that. So I'm going to leave it there at that. If the math is ugly, I get it. If it's ugly to you, it's not real pretty. So you just deal with it, just work with it and deal with the math and make the best use of all of the skills that you have with regard to your partial fraction expansion and your denominator terms and your numerator terms. Just work through that. Okay, go ahead and let's look at another problem that we had here. Any other problems in the homework assignment that you'd like to see worked out? Okay, well, I'll choose a couple of them for you. And by the way, if you have problems on any other homework assignments that we've had that would help you in preparation for the exam, let me know. So let's go ahead and let's take a look at what we have for numbers. We had 4, 9, 19A. Let's take a look at energy stored. Actually, let's do 38. Because that's a mutual inductance problem. Before we end class again, I'll remind you of the things that are on the exam that are worth reviewing, and mutual inductance is one of them. So let's look at problem number 38. And in 38, I asked you to do A and C. 38, A and C. So let's draw the circuit for 38. So we have 180 volts here. And then there's a switch in the circuit. No energy stored in the circuit at the time the switch is closed. There's no energy in the circuit. The switch is closed. So we're looking at T greater than the switch is closed. And then we have a 100. And then we have an inductor. And the inductor is 15 henries. We have a dot here. And then over here, it's 10. I don't know why I wrote the henries there. We don't tend to do that. And then the dot is on the bottom. And then I have 40. 160 plus minus V0. That's our circuit. Okay, and it says we're going to find V0. So this is what we're after, V0. That was part A. And C, this problem is find little V0. Okay. Let's stare at this for a bit. We haven't seen mutual inductance in a while. So how do I know this is mutual inductance and not a transformer? How do I know that? How do I know to solve this problem using the mutual inductance rules and not the transformer rules? Because if this was a transformer, we could transform this impedance and bring it over to the other side. So there's several things. Number one is we have values for these inductors. For a transformer, the inductance value goes to infinity. So you would never have an inductor value labeled on a transformer. Instead, you would have this ideal transformer. We don't have that here. So we would have that. We would definitely have the dot notation. We'd have the 2 bars. And then we have to have a turns ratio, N2 to N1. So it might look like this, 1 to 100. For example, so that gives us the turns ratio, that gives us the value of A. Okay, so we don't have any of that. And so we're just gonna solve this problem like it's a regular problem with just mutual inductance. Okay, so what's the first thing we should do? Step one. Wrap up the test and go home. Step one. I know how to
Do
solve
we
these
convert
problems.
everything?
Yep, that's correct. We convert everything. So let's go ahead and do that. So look, this is a little tricky. It's not, it's tricky. It's listed as just 180, okay? But the way you need to see this, it's for t greater than 0. See if you agree that 180 is really 180 u of t. Do you agree with that? It's only valid for t greater than 0. The switch closed for t greater than 0. So this is 180 u of t. So when we convert that, that's going to convert to 180 over s. We have a 15 Henry inductor. That 15 Henry inductor is 15s, 20s, V0. Resistors don't change, but this, don't forget, that's just like an inductor. Don't forget that, just like an inductor. So when we're in sinusoidal steady state, we use j omega m. Here we use ls, or in this case, ms. Okay, so there's our circuit, all transformed. Now what? Well, see the mesh analysis and nodal analysis. Well, I think we want 2 loops. That's the easiest way to solve this thing. So there's this loop over here. Let's just call that I1. And this loop, I2. And this is the beauty of these, quote, transformers. I mean, this in essence is just like a transformer. It's you isolate. Notice this part of the circuit it's isolated from this one. This is what the two have in common. That's what bridges them together. But they're isolated. None of the current I1 at all is seen over here in this region. None of it. Okay, so let's go to I1. Let's write our equation. Minus 180 over S plus 100 I1 plus, now we got to get this right, 15S I1. That's the easy one. Now it's the mutual inductance term. So the mutual inductance term is 10S, and it's going to be multiplied by the current that goes through the other inductor, and that current is I2. Now the question is it positive or negative? And the answer is it's going to be positive because I2 goes in the dotted side, I1 goes in the dotted side. So they both affect in the positive manner. So the I1 and I2 are both going into the dotted end. If they both went to the dotted end or they both go into the undotted end, it's plus. Otherwise, it's negative. Great. Sum that up. It's equal to 0. Well, let's see. This looks like a 5. We can definitely divide by 5, and we can multiply by S. So we're going to times S over 5. Okay. So if we do that, we're going to clean up the S in that first term. You can see that. And then we're going to have that 180 that's going to be divided by 5. And 180 divided by 5 is going to be 36. So this is going to be negative 36. Now, 100 divided by 5 is 20. So it's going to be 20S I1 plus 3S squared I1 plus 2S squared I2. And that's going to be equal to 0. So let's clean that all up. So our I1 terms For I1, we're going to have 3s squared plus 20s I1 plus 2s squared I2 equals 36. I'm just going to play one more game with this here, and let's just get pulling s out. S times 3s plus 20 I1 plus 2s squared I2 equals 36. Let's hold on to that. So there's one of our equations. The I2 equation's not much more difficult. All right, let's pull it down far enough so we can see it. Okay, I'll start at the top. 40 I2 plus 160 I2 plus 20s I2. Same thing. Now I have to get the mutual term. So the mutual term is plus 10s, and now it's I1, and it's a plus because, again, I1 and I2 are both going into the dotted terminals. Sum those up and they're equal to 0. Let's see, you can get rid of this and this and this and this. I can also divide by 2. I think that's as much as I can do. So divide by 2, 22 plus 8I2 plus SI2 plus, what did I divide by 2 for? That was dumb. I'm sorry. This is a 1 right here. Forget that. Don't do that. Let's leave it just like this. So let's group my I1 and my I2 terms. I1, S I1 plus I2. Let's see, 4 and 16 is 20. 2S, pull out a 2 here. 2S plus 10 I2 equals, and 0 divided by 2 is still 0. Isn't that a thing of beauty? Okay. That's more like a homework problem. The math isn't so ugly. So what are we solving for? Well, we want V0. So V0 is clearly 160 times I2. Excuse me for a moment. Let's just take care of that. Okay, so we want to solve for I2. I2 equals bloop, bloop, over this. Start with the denominator first, because I always do. S, 3s plus 20. I don't like the looks of that. 2s squared, s twice, s plus 10. Okay, and in the numerator, since we're solving for I2, we replace by 36 and 0 over here. S, 3s plus 20, and s. Okay, numerator easy, minus 36s. Denominator, not so easy. 2s cubed. Somebody doesn't want to go to voicemail there. Okay, 2s cubed minus 2s. That's good. I can factor out a 2s. That's going to make life easy for us for the factoring world. S plus 10, 3s plus 20. Okay, now it's just cleanup time. Equals minus 36s. Now that s is going to cancel in the numerator with this. So I'm going to factor an s out. I'm going to factor one s out, and I'm going to actually factor a 2 out also. So when I do, I have s squared. Now, so this is factored out, so minus. So I have 3s times s, that's 3s squared. And then I have 20s plus 30s plus 50s plus 200. Okay, cancel, cancel. 18 equals 18 divided by s squared minus 3s squared. Everything else is going to be negative. So here's my negative, and I lost this negative in the numerator. That's going to cancel with this negative in the denominator down here. So leave that negative there. And then it's going to be 2s squared plus 25s plus, not 25s, 50s plus 200. Okay, plus plus. So I'm going to factor out a 2 in the denominator. That'll bring that to a 9 in the numerator. Factor out the 2, s squared. There's my 25s. And that looks like nice factors. Wow. Equals 9 over s plus 20, s plus 5. Okay, so that's I2. Remember, V0 is equal to, we said 160 times I2. 160 times I2. So let's go ahead and get that. V0 is 160 times I2 equals 160 times 9 divided by s plus 20, s plus 5. Okay, that's not bad. I think we've got all that squared away. Okay, so let's continue with this, minus 36s, good, 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 good. Okay. All right, so partial fraction expansion then. So this is equal to A over s plus 20 plus B over s plus 5. A equals s plus 20 times V0 of s. Actually, this is the answer to part A. That's V0. Evaluated when s equals minus 20 equals. So for clarity, I think some of you are a little confused about what's going on when we do this. So what we're doing is we're multiplying this by A's denominator. That's the only term that disappears when we do that, the s plus 20. All the other terms remain. 160 times 9 over s plus 5. And now I substitute in s is equal to minus 20. This is 160 times 9 divided by minus 15. Divided by minus 15. So let's see. 3 in here gives me negative 5, gives me a 3 there. 5 goes into 180. I'm sorry, into 160. So 5 goes in there. What do we have? 32 times? So 32 times 3 equals 96 with a negative sign, negative 96. A equals negative 96. What about B? B is equal to s plus 5 times V0 of s, evaluated when s is equal to minus 5. This time I'm looking at this same thing, and instead of this one canceling here, not that, instead of this s plus 20 canceling, this cancels this time. So what's left? 160 times 9 divided by s plus 20. That's what's left. Evaluated when s is equal to minus 5. This is equal to 160 times 9 divided by a positive 15 this time, which is obviously equal to a positive 96. So let's answer the problem. V0 equals, well, it's minus 96 divided by s plus 20 in the frequency domain. That's going to be minus 96 e to the minus 20t. Then plus 96 e to the minus 5t. And then if you like doing that free of charge, put a u of t at the end. And that is a voltage that is in volts. Okay, I want you to note that there is only continuous response. Why is there only a homogeneous response? Well, let's take a look at this circuit. DC inductor. So the way that energy gets from this side to this side is through this inductor. And what does that inductor look like to DC after long enough time? It looks like a short circuit. What's the voltage across there? There is no voltage. So it's inducing nothing over here. Okay, so you're not seeing that DC part. You're not getting a DC part. That's why there's no DC. That's why all you have is a homogeneous response in this particular circuit. Okay, so that was a good mutual inductance problem. Let's see what other problems that we might have. Let's see, we've had an op-amp problem. We could do that one. Let's do another convolution problem. Let's look at 1363. So these are two fairly simple functions. These are really, really easy functions. It doesn't matter if the functions look a little more difficult. Watch how this process works. So this is a convolution problem. And in 63, we are doing B. So B looks like the following. So for B, we have an h of t, part B is from 0 to 10. Actually, let's put some color on this. So this is h of t, and h of t goes up to 4, and it extends for 10 seconds. X of t for this problem is the following. A real easy function. So x of t goes from 0 to 40 is height of 1, kind of height of 1. It goes out like that. So this is 40 out here. Height is 1. Okay. So that's the first thing that we want. The next thing that we want And most of the times you don't even have to draw this, but I'm going to draw it on the same graph in color. I've got to flip one of these. I need, so the first thing I want to do is I want to change this to the tau axis. Ready? I just did it. Do you like this? See how I just changed it to a tau axis? Now I want h of t minus tau. So h of minus tau is flipping this across the axis. So it's going to look like this. It's going to be on this side. Then h of t minus tau is just to shift it by t. So h of t minus tau, let's draw that here in blue. Let's put it in some random location. This front edge is t. It's not always t. It's t plus whatever this edge is when you flip it. And then this one is going to be t minus 10. Because when we flip it, this is going to flip over to here. It's going to flip to minus 10. So it's t minus 10. This height remains at 4. And this is the tau axis. This is h of t minus tau. I could have flipped x. It would have been just as easy to flip x. Do not flip uglier functions. Flip easy functions. Okay, regions. We're going to have the same sort of thing. Region number 1 is going to be the no overlap region. And that's going to happen for all t less than 0. You can see that. This front edge is at t. When all t is less than 0, we know that the constant, which is going to be y of t, is at time t, for t less than 0, it's the integral from, we had been talking about from 0 to infinity of x of t, x of tau, h of t minus tau d tau. And we know that this is going to be 0 because a typical picture looks like the following. Typical picture. Over here on this side, this goes there. That's what that one looks like. This is what the other one looks like. It's somewhere over here. And remember, we're multiplying the functions together, multiplying them, and then integrating the multiple. So when you multiply this, all of this 0 times the green 0 is 0. This 4 times this 0 is 0. This 0 times 0 is 0. This 1 times this 0 is 0. It's 0 everywhere. That's why it's equal to 0. So that's the first region. Second region is with the partial overlap. And that's going to happen when? Well, when t slides and gets, when this is sliding in this direction and gets to here, that's when t is 0. But then this back edge, we're going to partial overlap. This back edge is t minus 10. Don't forget that. This front edge is always t, always. So as long as t minus 10 doesn't equal 0, so this is going to be for 0 less than or equal to t, less than or equal to 10. So typical picture, we'll draw a typical picture. Typical picture. So this is, and this other one is something like this. Red. Front edge is t, trailing edge is t minus 10. It will always be. This over here is 40, just like it was 40 there. The only time that you have some overlap is in this region from here to here, from 0 up to time t. That's the only time we get a product of those two that is non-zero. So remember, this height is 4, this height is 1. These are easy functions. So this is going to be equal to, in this region, it's the integral from 0 to time t, and it's going to be x of tau, h of t minus tau, d tau. Well, what are those functions in that region? X of tau is 1, h of t minus tau is 4, and then I integrate. 4 times 1 is 4. 4 tau evaluated from 0 to t equals 4t. So that's our second region. Third region, full overlap. They don't always work like this. What could happen is we could end up with some, we can go from partial overlap right into partial overlap. You don't always necessarily have full overlap. It doesn't happen. It just depends upon the function. Now that's going to happen as long as this full overlap is going to happen for 10 less than or equal to t less than or equal to, once t gets all the way up to right here, then we're going to have the full overlap. So that's going to be 40. So from 0 to 40, typical picture. So a typical picture looks like so that's the green function. The red function is in here somewhere. Draw red. So the only time we get anything non-zero region between t and t minus 10. So the integral is going to be, this time it's y of t is equal to the integral from t minus 10 to t. But this is a beautiful thing. Just going to write the functions in. We know what these functions are. One of them is 1 and the other is 4 in that region. D tau equals 4 tau evaluated from t minus 10 to t equals 4t minus 4 times t minus 10. 4t minus 4t, cancel, cancel. And then I just have plus 40. Check boundaries if you want to. When t is equal to 10, 40. So you can check boundaries as a check. Now we're going to go to partial overlap. This has made it to here at the end of this region. Then it's going to pull out and part of it's going to overlap again. So 4, we're going to go to partial overlap. And that's going to happen for what range? 40 less than or equal to t, less than or equal to 50. What does that typical look like? Typical picture. Following. That's the green one. Here's your red one. From here to here is the only place that anything is happening. Otherwise, all multiplication is 0. So that we know, let's get those values in there. Okay. This is right here. That's t minus 10. Don't forget that. This one here is 40. So we're going to integrate from t minus 10 to 40. So y of t equals the integral from t minus 10 to 40 of what numbers? The same darn numbers. Are you sick and tired of this one? It's too easy. So it's 1 times 4 d tau. We've integrated that a bazillion times. It's still 4 tau evaluated from t minus 10 to 40. This is equal to 4 times 40 minus 4 times t minus 10. That equals 160 minus 4t plus 40 equals 200, 200 minus 14. 200 minus 14 in that region. Again, do a little quick check. The boundary was up here for this one was 40 seconds. 40 seconds, right here when we put in 40, 200 minus 4 times 40, 200 minus 160 is 40, and that's going to match with the 40 that we have at the end of that region. And then finally, the last region is the no overlap region, which is, this is 5, it's no overlap. And that's going to happen for t greater than or equal to 50. And this one's so easy, we're just going to write it down. Y t is equal to 0. So what happens in that region is the following. It looks like this. So green looks like that. That's your green. And red is out here somewhere. No overlap. So everywhere you multiply those, you get 0. 0, 0, 0, 0, 0. It's 0. So we put that all together and we can sketch it. So overall, y of t is equal to, it's all these different functions for different values of time. So we know the first thing is it's 0, 0, or t less than or equal to 0. We know that. And the second region was, scroll back, 4t from 10 to 40. Or t from 10 to 40? From 0 to 10, we're missing 10. 4t from 0 to 10, that's better. 4t from 0 to 10. 4t, okay. Then we had a fixed amount. I believe that amount was 40, is that right? 40, and that was from 10 less than or equal to t, less than or equal to 40, if I remember correctly. Then we had another function. I don't remember what the function is, but that's from 40, less than or equal to t, less than or equal to 50. Let's get that function. That function was from 40 to 50, 200 minus 4t. And then it's 0 for t greater than or equal to 50. Let's sketch it. $10, $20, $30, $40, $50. Okay, 0. 0 up until then. 4t. So when I get to 10, four times 10 is 40. Let's make that 40 up there. And what's going to happen is this is a straight line equation. I think you all know a straight line equation. Straight line with a y-intercept of 0. Then it stays 40 all the way across until it gets to 40 seconds. So it stays like that. And then 200 minus 4t, believe it or not, is a sloping line just like this. This line would continue. If it were to continue, it would intersect the y-axis over here at 200, sloping downward. Slope was minus 4, and then 0. There's our function. This is y of t. Sorry, not x of t. This is y of t. That's the output. Comments or questions on that convolution? Okay, let's take a 5-minute break. Let's come back. And once we come back, we'll see if you have any other questions or any other problems you'd like to look at. Okay, we're back from break. Comments, questions, concerns, things you'd like to look at? Continue focusing on problems. You want to continue to look at some problems here. Let's go through the exam. I'm going to stare at the exam here while I'm chatting with you, just so you get a sense of these topics. So, working with second order differential equation, homogeneous response, natural response, characteristic equation, homogeneous equation, forcing functions, forced response, initial conditions, mutual inductance, transfer function, finding a transfer function, just complex numbers, working with complex numbers, polar form, rectangular form, phasors. You can imagine most of the work is in phasor and Laplace world. So phasors, sinusoidal steady state responses with phasors, obviously. Superposition, when you have sources that are sinusoidal and they have different frequencies, you must get the answer using superposition, must. Using Laplace transform properties, knowing some basic transforms, and then using properties to find the Laplace transform of an overall function, being able to find poles and or zeros. There is one throwback problem. I give you one circuit, and in that circuit, I say, here's a circuit, write the nodal equations. Same circuit, write the mesh equations. Do not solve the equations, just write your mesh equations, just write the nodal equations. And then what would you do if I asked you to solve for this voltage or this current? How would you do it? Okay, so it's just mesh analysis and nodal analysis. You can't escape without knowing how to do that. An impedance or an admittance problem. How do you work with series parallel? Given a function in the frequency domain, use partial fraction expansion to solve for the time domain function. Convolution problem. Problem where you'll have to develop the second order equation from a circuit. So it'll be a circuit analysis, find the second order differential equation. There will be a circuit analysis using Laplace transforms in which you will have to include initial conditions. So energy stored in inductors and capacitors. How do you put that in the entire model when you're modeling your circuit? And then finally, there will be an ideal transformer problem. Those are all the problems on the exam. And again, it's select from those problems that you have, select. So there are 12 of them, select 10. Any questions on any of that? Any questions on what I meant by any of those things? Like, I don't, what do you mean mutual inductance? Any questions about any of that? Okay, hearing no questions, let's just continue. See if we can work a couple more problems here. And were there any questions on the homework that we handed back from chapter 12? Any questions on any of those problems? So if you have any of those, let me know. Now's the time to sort of focus on it. All right, let's look at problem number 9. Problem number 9 says the switch in the circuit shown has been in position X for a long time. So let's draw the circuit. So this is 625 nanofarads, And this is where the switch is. So the switch is over in this position, and it's going in this direction at t is equal to 0. $5K. .5 Henrys, 2.5. I don't know. Your author does that a lot. You know me, I like numbers. 5 halves. V0 is given over here. Okay, so let's see what it says here. So the switch has been in position X for a long time. Position X, position Y. It's been in position X for a long time. What does that mean to us?
Steady state.
Excellent. See, there's a DC input. See, this is DC. So this circuit is operating in DC steady state. At t equals 0 minus, the circuit is in DC steady state. Why is that important to us? What can we find? Well, what we can find, if the circuit is in steady state, is we can find the voltage across the capacitor and the current through the inductor. That's what we can find. Tell me what IL at 0 minus is. So remember, at 0 minus, that's what we have.
0.
Good. How easy is it to figure out what is VC at 0 minus? Be careful as you look at this. So what does that inductor, what does the capacitor look like at 0 minus?
Open.
Excellent. Open circuit. No current's flowing through there. So all the current is just doing this, correct? So if it's doing that, I get a voltage across this resistor, which is the same as the voltage across the capacitor. And that voltage is 150 volts. Everybody like that? So what's VC at 0 minus?
$150.
Plus, minus, minus, plus. Okay? If you write that equation around that loop, it's negative 150. And we know IL 0 minus is 0. So those are our two conditions. Those conditions are valid for t is equal to 0 plus. So the switch gets thrown, and the circuit now looks like the following. It's over here and not where the red is. So now it looks like that. So this thing over on this side, this current is just going around in a loop doing nothing interesting, but this is its own circuit right over here. So we're going to draw that circuit for t greater than 0 and then analyze it. Okay, here is the capacitor. We know the model for the capacitor, we have the initial conditions. So the model for the capacitor is a capacitor and the initial conditions. Do you remember the equation for the voltage source? If you do this with a voltage source, do you remember the equation? What is the value of the voltage source? So we know, for example, this is going to be 1 over CS. CS. What's this equation? Let's write that so we can all read it. What's the equation for this, for the voltage source? It's going to be V at 0 over S. V at 0 over S. All right, well, we have V at 0. V at 0 is negative 150. Negative 150 divided by S. So it's going to be that. 1 over CS, it's a little bit of an ugly number. Let me just punch this in my calculator here on my computer. So I have 625 nano. So 625 minus 9, and then do the inverse of that. And that's an ugly number. So let's right now, let's leave it at 1 over 625 nano S. It's still a pretty big number. Okay, so this, from here to here, that is the capacitor. From here to here is the capacitor. This, that's not the capacitor right there. The model is both of them, the initial condition and the capacitor, the energy stored. If we were looking for the voltage across the capacitor VC, not that we're after that, but this would be VC up here. We're not looking for that, but that's what VC would be. Okay, let's continue with this circuit. $5K. Here's the inductor. And here's the source for the inductor. This is an easy source for the inductor because the initial condition is 0. And so this is L, I at 0. So I at 0 is 0. IL at 0 is 0. Put down, there's IL at 0. So that's 0. So this is a 0 volt source. That's uninteresting. 0 voltage is the same as a short. I could just short that out. I don't even need to have that there. Okay? So let's just get rid of it and not even put it in there. And then this is LS. This is 5/2 S. So that is the entire circuit. And then the voltage, V0, is this V0 right here. And so for this problem, for problem number 9, that's what we want to find. We want to find V0 in the frequency domain and in the time domain. In the frequency domain and the time domain. All right, so let's work our way towards finding that. Okay, so it's a single loop. That's pretty darn easy. In fact, there's only one source, and that source comes from the energy stored from the capacitor. So we can find this voltage right here by voltage divider or by finding this current. I'm going to choose voltage divider. So this voltage here splits up. Some appears here, some appears there, some appears here, but all three of them are in series. So V0 by voltage divider is 5/2 S divided by, just writing them in order, doesn't matter what order, I write them in. 5/2 S plus 5K plus 1 over 625 nano. That's that, all multiplied by the current. And the current, I'm sorry, the voltage source. And the voltage source is minus 150 over S. And I missed an S here, right there, that's an S. Okay, so now look, it's just number crunching. Use a calculator, use whatever you need to use. This is going to boil down to the following. This is going to be equal to minus 150 S divided by, so we're going to divide, we're going to multiply this S down in the bottom to get rid of this S in this denominator. It's going to give us an S squared. We're going to pull out a 5/2, and you'll end up with this if you do the math. That's still a big number there, so we'll still leave it there. 640K. So multiplying the s through the denominator is what I'm doing. And then I'm pulling out a 5/2 out of both the numerator and denominator. I'm factoring out a 5/2. Okay, well, this can factor. And not that I know the factors off the top of my head, but the factors are s plus 400, s plus 1600. So I have minus 150 s. So this is our V0. Well, what are we left with doing? Partial fraction expansion. Okay, A is equal to s plus 400 times V0 of s, evaluated when s is equal to minus 400. Evaluated when its A's denominator is equal to 0. A value of s that causes A's denominator to be 0. This is equal to minus 150 s divided by s plus 1600. Evaluated when s is equal to minus 400 equals minus 150 times minus 400 divided by minus 400 plus 1600, 1200. Equals 150 over 3 equals 50. Nice numbers. B is equal to s plus 1600 times V0 of s, evaluated when s is equal to minus 1600, and that is equal to minus 150s divided by s plus 400. Minus 150 times minus 1600 divided by minus 1600 plus 400 is minus 1200. Let's see. 400 goes into 1200 3 times, 4 times, 50 times. That's equal to, let's see, I have 3 negatives there, so it's a negative 200 equals negative 200. So phi0 of t is equal to 50 e to the minus 400t plus a minus 200. Let's make it a minus right now. Minus 200 e to the minus 1600t. The units of this are volts. For the heck of it, I'm going to put a U of t here. If you don't, I'm not going to penalize you. It's nice to put it there in volts. And that's the answer for V0. Notice, by the way, this circuit was much more realistic in terms of values of the capacitor, inductor. Look at how fast this disappears. This one decays slowest, this decays faster. So this term hangs around a long time compared to this one. Still, that time constant is really, really fast. Really fast. So it's not even around a millisecond. It's gone real fast. Okay, we probably have enough time to look at one more problem. Let's take a look at which of these problems might be most beneficial to you. There is no op-amp, by the way. There's no op-amp problem on the exam, so you don't have to worry about op-amps. Let's look at this one. 13.5. So we have the following circuit, or portion of a circuit. and then 250 nano. Series RLC circuit. There's the parallel, and then there's the series RLC circuit. Okay, on this problem, number 5, it says to express the S-domain impedance of the parallel combination, and then give the numerical value of the poles and the zeros. So we want the impedance. So let's get these values in there, 6.25, 250 nano. Now, some of you would approach this by going right to the impedances, converting these to impedances. But let's write down their impedances so that we have them. So we know this one here is going to be 6.25S. This one is going to be 1 over 250 nano times S. And this is 2K. That's in terms of impedances. But what if we did them in terms of admittances? So green is admittance. So never be afraid to look at admittance. Sometimes it makes the problem solving easier. Red is impedance. When you're in a parallel situation, especially when you're in the S domain, it's usually easier to do the admittance because we know the admittance is all add. So what we're looking for in this problem is we're looking for this. ZAB. And this is what I'm going to solve for. Right now, first thing I'm going to solve for is YAB. And the reason is because YAB is 1 over 2K plus, remember, admittances add when they're in parallel. That's the beauty. And we know adding these numbers is a heck of a lot better than product over the sums and then product over the sums, doing it twice. Okay, so let's see what we have here. This is equal to 1/2 milli. That's this one. 1 over 6.25. Well, 6.25 is kind of an ugly number, but if you end up looking at that, 1 over 6.25 is 0.16. So let's write it this way right now, 0.16 divided by S. Or you could write it as a fraction if you want to. And then I have plus 250 nano times S. Okay, just cleaning it up a bit. Common denominator equals 1/2 milli times S plus 0.16 plus 250 nano times S squared. So that is our admittance from A to B. Clearly, hopefully clearly, ZAB is equal to 1 over YAB. This is the only place that admittances are nice. It's when we have parallel circuits. So that's just going to flip this whole fraction. So writing in order, 250 nano times S squared plus 1/2 milli times S plus 0.16. And obviously the author put these numbers in here for a particular reason, because you can now clean this up. We're going to clean it up by doing what? We're going to divide top and bottom by, we're going to do this, 1 over 250 nano, 1 over 250 nano. We're going to do that to clean out this lead coefficient. So when we do, we end up with the following. 4 meg S divided by S squared plus 2000 S plus 640K. Looks familiar. So that's ZAB. That is in ohms. Find the poles and zeros. And then let's see what the poles and zeros mean. That's interesting as well. Okay, so the poles and zeros. Zeros are easy. There's only one. 0 at S equals 0, right? That's what causes the numerator to be 0 when S is 0. So there's a 0 there. That means when S is 0, that's DC. At DC, this impedance is 0. That's what it says. At DC, this impedance is 0. Well, let's look at that. At DC, oh yeah, that acts like a short. Oh, a short in parallel with everything is a short. It is indeed 0 at DC. Now, let's take C of S and factor it as we did before. S plus 400, S plus 1600. And of course, the numerator is the same, 4 meg, which is just a multiplicative constant times S. So the poles are at S equals minus 400, S equals minus 1600. If anybody wants to know what that means with regard to the poles, if you put in the following input, something, any constant, A, e to the minus 400t, some interesting stuff will happen. If you put in any constant, B, e to the minus 1600t, you're exciting that at a natural frequency. That's what's going on. Those are your natural frequencies. They're from a homogeneous response. So those would be the values of the poles and the zeros. What are the units? We didn't talk about that. Remember, S is a natural frequency. It's radians per second. Same up here. Radians per second. That's the units of S, radians per second. Okay, that was hopefully enough of those problems in that chapter to help you understand what's taking place with regard to any problems that you might see on that chapter. I'll entertain any questions before we call it quits for the day. Any questions? Questions about the exam tomorrow, how we're going to go through the exam. I'm going to send it to you. Everybody will turn their cameras on so I can sit here and observe you like I would as if I was in a classroom. So your cameras are on while I can watch you take the exam, because I know a lot of things that can happen if I am not able to observe you. So we don't want that to happen. If you don't have a camera, you need to make an alternate arrangement with me to take your exam. We'll get you a different exam or a different time. We'll do something. Any questions whatsoever? Okay, Jack, you managed to get everything you needed from either the video yesterday or you picked up the components from someone else? Yes?
Yeah, I got it, yeah.
Okay, terrific, fantastic. Well, all of these videos are out there if you need to look them up. If you're not sure how to find them, go to our Blackboard shell, okay, for this course. All of the links are there to all of the videos. You can find any of the videos that you need. Till tomorrow, study hard. Look forward to seeing you tomorrow. Stay away from people. Stay safe, stay healthy, and be prepared to do well tomorrow. Look forward to tomorrow. Okay, well, take care all. I'll see you tomorrow.